Alright, in this video it is time to begin building paths. If you remember in the last video, we had pointed out how a path could be generated from the goal node that we had found back to the start node. We had pointed out how the parenting indicators were working and even traced an imaginary path from the goal back to the start. In this video, it's time to build an official routine that will take that information into account and build a real actual path. Now before we get started, I want to point out one thing, and that is here in Visual Studio I have closed out some of the extra classes that were open, since as we were creating new classes, things started to get a little bit cluttered. So all I've done is closed out the series of classes, things like the old input systems, and so on, leaving open only a handful of classes that are relevant to the things we are addressing right now. So, to get started, you can see that we are already inside of the A star step class, and it is inside of this class that we will build the path itself. Also noting the fact that we're sitting here right underneath the continue method. So if we go down here and jump down, now we're right below the continue method, we can begin a new method. We will build a method called build path, and it will be build path's job to walk from the goal node back to the start node and assemble a path as it goes. So let's drop the structure of this method in place. This will of course need to be a static method. We will use this method to actually return the path itself. So we're going to give a return type of list, giving type node. So we will return a node list. For the method name, we will use build path. And build path is going to take in a node. We need to tell build path where to start building. And this will actually be building from the goal node. So we'll drop in a single node parameter as goal. Then we can throw in our braces for the method, and we're ready to begin working on the method itself. Now, in order to satisfy this return type of returning a list of nodes, we're actually going to build a list of nodes right here inside of the build path method. So we'll make a variable here, which is a list of type node, and we will call this variable path. Then we'll turn around and instantiate a new node list. So we have a list that we can start adding nodes to in order to build this path that we're getting ready to return. Alright, now we need to address moving from node to node by the parent links. We're going to build a routine that will address a specific node. Basically, we'll make what we will call the working node. And to do that, I'm going to make a node variable, simply called node. Now, this working node needs to start somewhere, and we know that we're building backwards, so we're starting at the goal node. So to begin with, we will initialize the node variable with the node goal. Alright, now that we have a node to start with, let's put together a while loop that will continue to walk node by node all the way to the beginning of the path. So, we will create a while loop, and we want this while loop to continue running as long as our node variable is not null. So as long as we have a node to continue walking to, we will continue running the loop. So while node is not equal to null, then things will continue. Now inside of this loop, we need to take the node variable and add that to the path. Since of course it begins at the goal, the first thing we need to do is include the goal itself in the path. So that means we will take our path and we will add the current node. Then on subsequent iterations of this loop, nodes will continue to get added to the path. Now, in addition to creating the path that can be used by navigation, we also want to indicate that this node here is now part of a path, so that our debug visuals will pick up on that and show it to us. So we can take this node and set its in path to true. Then one final thing we need to do in order to move on to the next node, we'll replace node with its parent. So we'll say node is equal to node.parent. So this is the point that we actually walk from the node to its parent. The parent becomes node and gets considered in the next iteration of the loop. Now we can see that the loop will terminate the moment we reach the start node, because if node was set to start, start's parent is null. We get around to the next iteration of the loop, node will of course be null, and we will terminate. Alright, now that we have assembled the path, the next thing to consider is the fact that the path will be in reverse order. You've solved the path from goal back to start, and so to put the path in order so that we can read it from the beginning of the path to the end, we will do a path.reverse. So now we can say path sub 0 is the beginning of the path, and then the very last node is the end of the path. Now I will note one thing very briefly here, and that is reversing it just to keep everything perfectly clear so that everything is more readable. If you wanted to slightly optimize this code and you were writing both the A-star routine and the path navigation for actors, you could leverage the fact that you know that paths are always backwards and simply have actors transverse paths in reverse. Navigate from the end to the start rather than from the start to the end. If you did that, you wouldn't have to run this reverse step here, and that would make the path solving more efficient. But again, in this case, since we're trying to keep everything clear, we're going to put this path in order just so that later on when we're talking about navigating paths in the AI navigation section, everything will make sense. We go beginning to end. But I just wanted to point that out. So if you wanted to begin optimizing, this would be a good place to start. All right, now that we have our path ready for use, we need to return that path. So we will return path from the buildPath method. That takes care of our return requirement, and that will also take care of buildPath itself. We have a routine which will now build a real, actual path. Now we need to decide where buildPath should get called from. Generally, you would want to build the path once you're done searching the node network, having found the goal. So if we look back up in the continue method, you can see that we do have a termination condition for the search. When the current node is equal to the goal, we know we found the goal and we're done searching. It is at this point that we will calculate the path. So what we'll do is we will say path equals build path, and then of course feed in the goal node so that build path knows where to start from, and that will create the path and store it in the path field. I'll note here that even though we're reusing the name path, in this case we are indicating the field that is part of A-star step. So, now that we have a path generated, it's time to test things out. So, let's build and run the game, and let's rerun the initial test. Let's take this far left node, then a node 2 away. Both of these selected will hit P. We begin searching from the left. All these nodes light up, and as we step through, we can see we continue searching outward from the start node until the goal is reached. You notice that moment that I hit that goal node, a path lit up between them. So we correctly found the ending condition, we found a goal, we assembled a path, and we marked these nodes as being part of a path. So our debug code is showing us that there is a path set up here. Of course, the search is terminated and we can't go on any further. So this is working very well, but let's put together some more interesting test scenarios. Of course, you saw the path that got generated was definitely not optimal since we went 45 degrees away from the node before turning back to it. So the question comes then, is this really a reliable way of searching? What happens if we get into more interesting scenarios? So, to show how things are working, let's set up a few different scenarios. As a matter of fact, let's make things one step more simplistic before we get more complicated. I'm going to move over now into the scene editor class, and I'm going to comment out the node deletion so that we have a full set of nodes in a grid. Now I'm going to start with a node 2 away from the left, and end with a node 2 away from the right. We'll hit P to begin a search, and in this case I'm just going to steadily step through the nodes that we search, just trying to note the direction that we're searching, to try to get a feel for that outward motion away from the current node. So if we begin searching, the first 8 nodes around the start are the ones that get selected. We have a lot of nodes on the open list surrounding those, and so those nodes are next up for exploration. So we find all those nodes in the next layer, so it's almost like we're advancing outwards layer by layer through all of our nodes until we search enough nodes to have finally reached the goal. The moment we reach the goal, then you can see a path gets generated back to the start. And once again, we have a very interesting path where instead of taking a direct route, the search code has decided that we need to go away from the goal and then back to the goal. So again, a very interesting result, but not something we're worried about yet since we're not weighting any of the search directions at all. So that's interesting to see how it's solving on a completely open grid. Let's bring our node deletion back in, and let's test navigating around some absent nodes. So let's rerun basically the same goal. We'll begin with the same 2 nodes. We'll hit P to begin a search. You can see once again we have the 8 nodes surrounding, and as we begin walking through nodes, we continue to walk outwards. Of course, we can't immediately walk as far in this direction since we're missing nodes. But we continue to walk, adding nodes to the closed list until we finally get past the obstacle on this side. And once we have searched enough nodes, the next node should hit the goal node. We get a path generated going back to the start. And what's interesting here is, again, even though the direction that we're drawing the path is just incidental from the way that we're searching, it actually does make a good path for these missing nodes. We properly avoid what could be viewed as a wall or an obstacle and reach the goal. But again, in a more complex scenario, we can see that our graph searching is still working just fine. Alright, let's put together a new scenario. Let's comment out the current code where we're building a grid and deleting nodes. For the next test, let's put together a scenario that is a smaller grid enclosed inside of a circle. So we'll actually need to make 2 calls to the node builder to build both a grid and a circle. So let's grab our node builder. We'll start out with the grid. We will call the build grid method. We need a position for this grid, so we'll create a new vector 2, and we'll give values of 320 by 220. For the number of nodes in X and Y, we will give 3 and 3 to make a 3 by 3 grid. Finally, our spacing we'll simply leave at 80. Now let's put together a circle. We'll grab our node builder. We will call upon build circle. For a position, we'll give a vector 2 of 400 by 300. For a radius, we will set a value of 200, and we will tell the routine to create 8 nodes in total. So having finished these 2 statements, we get the resulting scene. We have a 3 by 3 grid of interconnected nodes in the center, which are surrounded by a circle of 8 additional nodes. Now we can try an interesting scenario. We have 2 sets of paths that are not connected. So let's see what would happen if we tried to navigate from the top left corner of this grid out to the circle. We'll hit P, and we see that a search successfully begins. And if we continue advancing through nodes, we advance outward until we have covered the entire grid. Now if we continue to hit the spacebar, you'll notice that we do not search any further. And if we briefly look back in code, we can see that this is due to the fact that we have run out of open nodes. Here inside of continue, you can see that the moment the open list contains no nodes, we simply return. And this scenario is what we run into if we exhaust all of the nodes that we can move to and find no route to the goal. So in this case, we have failed to find a path. And you can see that reflected by the fact that as we hit the spacebar, nothing else continues. We can also note, looking at the state of these nodes here, all of them are on the closed list. They're all being marked by a closed marker. Because of that, we know that they have to get removed from the open list to get added to the closed list. So in a visual sense, we can see that there are no more open nodes, and that's why we cannot continue. Now let's make a slight adjustment to the node network. I'm going to grab this bottom node, hold Control, and grab the bottom node of the circle. I'll hit C to make a connection between these 2. Then let's rerun the original test, the corner of the grid to the outside circle. We'll hit P. We'll begin searching. And you can see we're filling out and closing all of these nodes. You'll notice that the moment we hit the bottom node, we have opened up this node on the outer ring. So having finished searching, actually let me reselect these. I don't need to hold the selection, of course, since goal and start are already remembered in A*, but I'll just leave everything in the same visual state. So back to the grid. You can see that all of these nodes are now closed. However, we have thrown this node on the outer ring into the open list. So that means he is now transversable. The moment we walk over to him, more nodes open up on the ring, and we walk back and forth until we find the goal node. The moment we find the goal, we're able to trace a path back to the start, and we have found a valid path. So in this case, we've hit the other terminating scenario, finding the goal, but since we found the goal, we can indeed make a path. So we've put all this together just to show that even in a more complex scenario, our graph searching algorithm is still able to make paths. Alright, there's one last test scenario I want to put together. Back in Scene Editor, let's comment out the grid and circle. I'm going to comment these rather than delete them, just in case we would ever want to test the scenario as we make our search algorithm more advanced. Now for the next test, I'm not going to create any nodes through code. I'm simply going to run and build a scene interactively here on a blank scene. So what I'm going to do is I'll hold Shift to begin creating nodes, and I will click out 4 nodes in a horizontal line. In addition to these nodes, I'm going to take the 2 middle nodes and add more branches to them. So from this middle node, we'll add 1 branch out. I'll reselect the middle node and create a second branch, and a third, and a fourth. Then I'll do the same thing to the second middle node, creating 4 nodes that extend from it. Now what we're going to do is we're going to solve a path between this node as the start and this node as the goal. The reason for doing this test is to see if the algorithm will handle a scenario where there are many possible dead ends. Looking at this scenario, we have 8 possibilities to dead end. If we hit any of these branching nodes off of the middle 2, we can't advance any further. So we're going to see if we're properly managing our open and close lists to know where we can always continue. So let's hit P, begin a search. You can see that the only node on the open list is that second node. So if we advance, we get more of the branches added to the open list, including the one that we do want to advance to. Now if we advance through a few more steps, you see we move forward, but the next nodes on the list are going to be these back here. And of course, each of those get considered and then added to the closed list. There's no further connection, so there's nothing to add to the open list. However, if we try to advance from this scenario, the next thing we do is find the goal. And of course, since the goal itself got added to the open list earlier, we do have nodes to move to. So we did not end up in a dead-end scenario since the new nodes kept getting added to the open list. So even as we exhausted all of the possibilities on this first step, we still had lots of possibilities, including the goal, still open. So again, just showing this to see that the search algorithm is indeed able to find paths in more complex scenarios. Now having done this test, I'm going to bring our original node grid back up, since it is this grid with the 3 nodes deleted from the center that we're going to use as we continue to develop the search algorithm. So with this now, we have put together the path building routine, and we have tested out the paths that get generated in various scenarios. So with that, that's going to wrap up this video.